video, we're going to be moving to the second step of writing Lewis structures. In the previous video, we looked at several examples of how to attach the skeletal structure together using guidelines to be able to do that. And now we're going to be moving to the second step of writing Lewis structures, and we're going to calculate the total number of valence electrons available for bonding. I want to remind you that we're going to be using the group number, the column number of the periodic table to find the number of electrons. If you have a cation, a positive ion, you subtract one electron for each of the positive charge, and if you have a negative ion, you add one electron for each negative charge. So for instance, the ClO3 minus, once we add up all the valence electrons, we'd have to add an extra electron because of the minus charge. It means it has an extra electron. Or if it's a cation, you subtract, positive ion, you subtract the number of electrons. So here's a couple of examples of this. For CH4, we're going to list out the number of elements that we have. So we have C and we have H. It turns out in CH4 there is one C and four H's. Now we're going to go and look at how many valence electrons each one of those elements has. So when we go and look up carbon, carbon is in column 4A. So it has 4 valence electrons. So there's one atom of carbon with 4 valence electrons. When we look up hydrogen, remember hydrogen's a nonmetal that belongs on the other side of the periodic table, but we have to put him in column 1A because it has 1 valence electron. So hydrogen in column 1A has 1, but there are 4 atoms of hydrogen. So this gives us a total of 4 electrons, 4 valence electrons for carbon, and 4 valence electrons for hydrogen. So the total valence electrons is 8. If we look at the next example, we have C and we have H also. There are 2 C's, there are 2 H's, and once again, there are 4 valence electrons for carbon because of the 4A. 2 atoms in C2H2, 2 atoms of H in C2H2, 4 valence electrons for carbon, 1 valence electron for hydrogen, and that gives us a total of 8 valence electrons, 2 valence electrons, 10 valence electrons. Then we go to XEF6. We're going to talk about how XEF6 is actually it doesn't follow the rules. It's an exception to the rules because Xe is a noble gas. So we would think Xe should not want to connect or bond with other atoms, but there are some exceptions in which it does. So Xe, and there is 1 Xe, and F, there are 6 Fs. And then we find out how many valence electrons each one of these atoms brings. Xe brings 8 because it's in column 8A. F brings 7 because it's in column 7A. That gives me 8 valence electrons. And then 6 times 7 is 42. So 42 for a total atom all up, the total number of valence electrons is 8. Then we've got carbon, and there is 1 of them. We have nitrogen, there's 1 of them. We have hydrogen, there's 1 of them. Carbon has 4 valence electrons, as we've looked at a few times now, within the 4A, column 4A. Nitrogen is in column 5A, so 5 valence electrons, and hydrogen's in column 1A. There is 1 carbon that brings 4, there's 1 nitrogen that brings 5, and there's 1 hydrogen that brings 1. That gives a total number of 10 valence electrons. Then carbon will have 1 valence electron, and then oxygen, carbon, 1 atom, oxygen, 2 atoms. So 1 carbon and 2 oxygen. And then each carbon brings 4 valence electrons. Each oxygen brings 6 valence electrons. 4 and then 12 give me a total of 16 valence electrons. And then finally, we have Sb and then F. There's 1 Sb and there are 5 Fs. If you can see the color code, I don't know why I didn't follow it on that example. And then on this last example as well. So Sb, when we look up Sb, technically Sb is a semi-metal, but we're treating him as a non-metal. 5 valence electrons. And then F, 7 valence electrons. So I have 5, 35 for a total of 40. So that allows us to count the total number of valence electrons. Calculate the total number of valence electrons available for bonding for that molecule. This final number is the total number of valence electrons available for bonding by adding up how many valence electrons each atom brings. The next step during this process is subtracting the number of skeletal electrons from the total number of valence electrons. Here is our skeletal structure, and I previously talked about each one of these lines is a covalent bond. Each line equals a covalent bond, which represents 2 shared electrons. So when we have the total number of valence electrons as 8, total number of valence electrons equals 8, and we're supposed to subtract away the number of skeletal electrons. When I originally connected this this molecule with the atoms, there is 2 electrons, 2 electrons, 2 electrons, and 2 electrons. 2 electrons for each one of these covalent bonds. So in this one, there is 8, 2, 4, 6, 8 skeletal electrons is 8. So when we subtract those 2, we end up with no electrons available for bonding. In the next example, the total number of valence electrons, equals 10, and the number of skeletal electrons, each covalent bond is representing 2 shared electrons. So this is 2 electrons, this is 2 electrons, this is 2 electrons. So we're going to subtract the number of electrons as 2, 4, 6 to give me a total number of 4 valence electrons remaining. Total number of electrons remaining as 4. So we're going to put down the total valence electrons as 8. We're going to subtract away the number of skeletal electrons. Skeletal electrons here, each one of these lines represents a covalent bond representing 2 shared electrons. So we have 2, 4, 6, 8, 10, 12. So obviously I made an adding error in a previous video. 8 plus 42 is not 8. 8 plus 42 is a total of 50, and I'm glad I saw that. I wish I would have saw it in the previous video. So 50 total electrons, and the skeletal electrons each counts as 2, 4, 6, 8, 10, 12. So we're subtracting away 12 skeletal electrons. Each one of these is a covalent bond representing 2 shared electrons. So now we end up with 38 total electrons remaining. And then total number of valence electrons equals 10. And then in the skeletal electrons, the skeletal structure, the electrons that we've already used. So the idea here is that we have a total number of valence electrons we should be using in this molecule, but I've already used some of those valence electrons in the skeletal structure. So I need to subtract them to figure out how many electrons I still need to put in for bonding. Once again, the idea is that I have a total number of valence electrons that I should be using in this molecule, but I've already used some of those electrons in terms of connecting the atoms. And in here, one bond is 2 electrons, another bond is 2 electrons, so 4 electrons, so we end up with 6 electrons between that is remaining to use for that molecule. The total valence electrons equals 16, but in the skeletal structure I've already used 2 electrons here and 2 electrons here, so the skeletal electrons is 4 electrons, so I have 12 electrons remaining. I have a total number of valence electrons of 16 to use in this molecule. In the skeletal structure, I've already used 4 electrons, so I still have 12 electrons to go. Then, total valence electrons is 40. The skeletal structure, I've already used 2, 4, 6, 8, 10. So now I have 30 electrons remaining to put in that molecule. I hope this helps with step 2 and step 3 of the process of writing Lewis structures. First, calculating the total number of valence electrons available for bonding, and then finding out how many electrons we have remaining to still put in this molecule by taking the total valence electrons and subtracting the skeletal electrons that we've already used.